asked for the energy levels. So they asked for an energy level diagram. So energy level should make you think of chemistry, so this should look pretty standard. The only tricky thing here is remembering that the higher energy is going to the bottom, because this energy is the amount of energy required to remove an electron. Think, what would you call this? Do you remember from chemistry? It has the word ion in it. Ionization. Yeah, ionization energies, right? How much does it take to make this electron leave? And when you get it to leave, then it's an ion, it's a charged particle. All right, and then the second part, they're asking, calculate the wavelengths associated with possible transitions between energy levels. So, obviously, the transitions are going to be like 3 to 1, 3 to 2, maybe 1 to 2, right? That's it. Here to here, here to here, here to here. And then all you have to do is say, okay, well, what is the energy level? Because what happens is something like an electron from up here falls to here. When it falls down to there, how much energy does it lose? What's the energy difference between 3 to 2? Eric, what? Yeah, 2 electron volts. And then that 2 electron volts is going to become a photon. And a photon has lambda. Right? So what we're saying is 2 electron volts, E is HF, right? And we're saying this energy, that's energy, by the use of Planck's constant? Yeah, I think it's Planck. By the use of Planck's constant, is going to allow us to calculate the frequency of light that comes out. Now, if I give you the frequency of light, can you give me the wavelength of light? Right? Because so you solve this, you say F is E over H. And then if I give you the frequency of light, how do you get the wavelength? You use C equals F lambda. Right? So then I just plug this in here, and then, or I can say lambda is C over F. And then of course that means I'm going to get lambda is CH over E. And E is that 2 electron volts. So there, that's how you get a wavelength out of this. When this falls down to there, it releases a photon which has 5 electron volts of energy. 5 electron volts through E equals HF gives you a frequency of light. And then by using C equals F lambda, I can get a wavelength. That's it, pretty straightforward. And they're all going to be pretty straightforward like that. You're just going to use those equations. So then C, the atom is in the ground state when the electron traveling blah, 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 collides with it, calculate, or can the electron excite the atom to n equals 2? So if you have an electron traveling at this amount, this velocity, what type of energy does it have? Hello, everyone? What type of energy does it have? Kinetic, right? So just find the amount of energy and see if that's enough. Right, so we go to C, we look at, calculate the energy, and we see 4.8 electron volts. Right? Well, how much energy, let me see what level this is. Oh, okay, so we want to go from 3 to 2. Yeah. Oh, sorry, no, just 1 to 2. Okay, cool, cool. So we want to just go from 1 to 2. And then 1 to 2 is only, how many electron volts based on our little diagram here? Is only, sorry, when I meant 3 at the bottom one. But yeah, the ground state is the one that's closest to the ground. So it's 1 to 2, and there's 3 electron volts difference. So then, all you do is compare your energy in joules, and this conversion factor is in the constants page that you're given. So you just say this compared to that. Because this is 4.8 volts, it's enough to get this thing to kick up to the second level from 1 to 2. Right? So they're showing us here, incoming, this electron's coming in at some velocity. It has kinetic energy. so that when it collides, it's going to kick this guy up. And it's going to kick this guy. It's going to give this guy 4.8 electron volts of energy. So is that enough to go up to the second energy state? Yeah, no worries, right? Is it enough to go up to the third energy state? No, because there I need 5 electron volts. So it'll kick it up to 2, but not to 3. So nothing super tremendously crazy here. Then another electron excites the atom from the ground state to the n equals 2 state, so 1 to 2. The atom then decays back to the ground state, emitting a photon. We just had this conversation. Calculate the energy of the emitted photon in joules. If it goes to 2 to 1, 2 to 1 means how many electron volts? 3. So then, I just calculate the energy of the emitted photon in joules by converting 3 electron volts to joules. That's all this is. This is a conversion. It's just, can you go from 3 electron volts to joules? And then that conversion is given. It's like 1.6 times 10 to the minus 19 electron volts per joule thing. Or no, whatever. It's given in your thing. All right, then in what region in the electromagnetic spectrum is this radiation? This is where you just have to remember stuff. You have to remember that the approximate thing. Now, the way that you can do this, right, the way I try to do this is if I look at the electromagnetic spectrum, right here in the middle somewhere is light. And light is 400 to 700 nanometers in length, in wavelength. Anything below that, anything below this wavelength, like this is actually higher energy, and this is lower energy. Because a longer wavelength means lower energy. So above this, like this is purple, so above that is UV, and then above UV is, I think it's something called, there's a small one in the middle. It's the one that I think they're using it to look inside your clothes. You know, at the airport? Oh, whatever. Next comes X-ray, and then comes gamma. So it's UV, X-ray, gamma. Okay? Then down here, this is red. So you get infrared, then you get microwaves, then you get radio waves. So, radio is all the way over here, X-rays all the way over there, visible light right in the middle. So all you need to do is we've calculated this energy, right? This energy was 3 electron volts? 3 electron volts? I don't remember. Oh yeah, it was 631, right? Okay, so this is 3 electron volts. So all you have to do is convert this into wavelength. Didn't we already do that? Right? We did it up there. So all you have to do is convert this into wavelength, and then from that say, is that wavelength bigger or smaller than visible light? Or does it fall in visible light? So we'll go over here, take a look. Yeah, okay, so yeah, okay, so there we go. We did our 3 electron volts, we just converted. So it's 1.6 times 10 to the minus 19 joules per electron volt. And then we get our energy. And then for here, you're just finding the wavelength of it. And when you find the wavelength of 413 meters, then that tells you it's violet, it's purple. So that's that problem. Okay, so that's one type. The types of problems that they'll have in this is they'll have light is energy problems, right? That's like this. Sometimes they'll have photoelectric effect problems where you have to use that equation. And then sometimes they'll have mass defect problems, right? Mass defect is where something breaks down and the amount of mass in the end is less than the amount of mass that you started with. What happened to the difference in mass? It became, you know, like when a nuclear bomb goes off? There's actually mass that gets converted into energy, and that's the explosion. All right, anyways, that's that first one.